last time we saw that there are two types of impact, direct central and oblique central. And the simpler version, 1D version, is direct central, where everything can happen along one axis. And so we are dealing basically with the scalar velocities. In this case, if you remember, there are two equations to help us solve the problem. One is the linear momentum of the system before impact is the same as linear momentum of the whole system after impact. Here we are using prime again, as after, and without prime means before impact. So this is one equation for the two unknowns of the problem, which are typically velocities after impacts. And then the other one we have is this parameter called coefficient of restitution, which is given to us. It is a function of the material involved in the impact, and in this course we consider it constant. It is actually a function of the relative velocity before impact as well as the material, but we neglect it in this course for simplifications. And this number, which is between 0 to 1 and is given to us, is equal to negative relative velocity after impact to the relative velocity before impact. And when this one is given to us, that's a second equation, which now we can, for using this one and the previous one, we can solve for, let's say, the two velocities after impact if the ones before impact are given. Okay, so we have two equations. In general, we learned that this E, if it's 0, means the impact is perfectly plastic, which means the objects stick together after impact. If it's 1, we call it perfectly elastic, which means no kinetic energy is lost and the objects will not deform as a result of impact. So now, before we go to oblique impact and look at the derivations of formulas for that, I want us to focus on one example together and basically study this problem together. So here, let's consider the example that I use in my dynamics classes for impact many times, and that is two cars collision problem. So here I have one car, and then I have another car. And it is a head-on collision. So here we have object A and object B, velocities before impact, and I'm trying to use realistic numbers here. So let's say you are on the highway and you have a head-on collision, and the velocities are, so you know, mile per hour when you convert it to, I'm trying to use SI units. So on the highways, if you go for 75 miles an hour, which is the speed limit in Arizona, 75 is 120 in kilometer per hour. And if you want to convert it to meters per second, you have to divide it by 3.6, which is roughly 33. So if I go 30 times 3.6 divided by 1.609 is about 67 miles, which is relatively good. So I say this is like 30 meters per second. And this one is, which is equivalent to what? Remember, 67 miles an hour. So this is a nice driver. It is not going more than the highway speed. And let's say B is. So B is going a little bigger. So B is going like 40 meters per second, which is like 89 miles, and that's not uncommon in Highway 17. So let's say you're going 40 meters per second. and this is off almost about 89.5 miles an hour. So one of them is overspeeding, the other one is not. And then the masses of these cars, again, let's say this one is the smaller sedan car is a ton, so 1,000 kilogram, and the bigger car is 2,000 kilogram. Okay, let's say it's a truck. And they have a head-on collision, and we want to find the velocities right after impact. And here we assume that the impact is plastic, but not perfectly plastic, and we come up with a number like, let's say, 0.4. So if in this collision it's E.4, it could be even smaller. What are the velocities after impact? And that's where we resort to our two equations. One is MAVA plus MBVB, which is the total linear momentum before impact, is the same as MAVA prime plus MBVB prime, which is the total momentum after impact. And then E, which is 0.4, is equal to negative relative velocity after impact, which is VB prime minus VA prime, divided by relative velocity before impact, which is VB minus VA. And we have to assume a positive direction for the x-axis. Let's go and say that the right side is positive direction. Okay, so now we plug in the numbers. This is 2,000. This number is 30. This is 1,000. This number, pay attention, it is negative 40 because it is to the left. And then this is 2,000 and this is 1,000. And these two numbers, I don't know, I have to find them. Similarly here, if I cross multiply, I would get VB prime minus VA prime is equal to negative 0.4 times VB minus VA, where VB and VA are, as you can see, negative 40 and 30. Okay? So if I simplify, I get to a 2x2 linear set of equations, which says 2,000 V prime B or V prime A plus 1,000 V prime B is equal to the left-hand side, which is 60,000 minus 40,000, so it's 20,000. And then here you will have V prime B minus V prime A is equal to negative 40 minus 30, that's negative 70. The negatives cancel, 70 times that's 28. Okay, so this is when you simplify. And now in the top equation, if you want, you can get rid of 3 zeros, right? So you can get rid of 3 zeros. So you get 2V prime A plus 1V prime B is 20, and this is negative 28. And if you call this positive 28, sorry, 1 and 2, all you need is subtract 1 from 2. Why? Because 1 has positive V prime, B has positive VP prime. So when we subtract, you're going to get 3 VA prime on the left, and here you're going to get negative 8, right? And so VA prime is going to be negative 8 over 3, right? If I am not making a mistake. Hopefully I'm not, and I don't think so. Let's just make sure. Doesn't look like to me, that's right. So this is like negative 2.67 meters per second. And if you plug this back into 2, you get VB prime to be 28 plus this number, which is going to be 25.33. Okay, so these are the velocities after impact. Does that make sense? Let's just again make sure we are not making any numerical mistakes. It's extremely important that we don't do it. So the top equation looks correct to me. The bottom equation I assume that is also correct. Yes, then you subtract. Yeah, it looks correct. So now, does that make sense? So car A was moving 30 meters forward. Now, after impact, it is negative 2.67. Negative means it's to the left. So after impact, it is going to be not only moving forward, it actually will be kicked backward with 2.67 meters backward. So it's a huge shock because you go from positive 30 to negative 2.67. So you have a total of 32.67 meters per second change in velocity. That's a huge shock, okay? And that will most probably kill any person. And here, V prime B, VB was negative, right? It was to the left, but now look, how much is this guy? Now this guy is going to be 5.33. This is huge. You are going from a big negative to a big positive number. This is 65 units change in velocity. So you clearly see that the impact is much harder for the smaller car. Although it has a little more velocity, but the change in its velocity all of a sudden is much bigger than the heavier car, and that's typically what happens, right? You expect that. The bigger cars get less injury compared to smaller cars. So that completely makes sense that head-on collision can be super dangerous. Okay? Now, I'll change this example to a different scenario for you. And this time, this is what we're going to do this time. This time I am going to clean off the sedan, and instead of sedan, let's say now the guy on the truck is not lucky to mess up with the smaller car. This time he is gonna be a head-on collision with a semi-truck. Okay, absolutely not good idea. So this time the mass of particle B is 20 tons. And let's say this is a semi that is coming with some similar velocity to 30. Let's say this time we make the semi to be the slower car. So we make this 30 meters per second or 67 miles. And we make the trucker to be the faster one. We make this guy go 40 and this one to be 89.5 miles an hour. Yeah, you can expect what's gonna happen, right? You go head on with a semi with such a huge speed. There is almost zero chance of survival, right? So what happens this time? All of these numbers are the same, except this time this 30 becomes 40. And then this MB is 20,000 and VB is negative 30. So your first equation will turn out to be $2,000, and if I get rid of 3 zeros, if you don't mind, it is going to be 2 VA prime plus 20 VB prime is equal to, so this is negative 600, right? I'm getting rid of 3 zeros. It's negative 600, and this is 80, so negative 520. And then here you will have this number is going to be the same. So now if you solve, and this time what you want, you cannot just subtract or add because the coefficients are not the same. So this time what you do is you multiply equation 2 by number 2 and then add it to equation 1, because now you're going to have 2 negative VA prime and positive 2 VA prime. When you add, they would cancel, so you're going to get 22 VB prime and then the number is going to be negative 520 plus 2 times 28, so 56 minus that, you're looking at negative 464, right? And therefore VB prime, the velocity of the semi after impact, is going to be 464 divided by 22, which is 21.1. meters per second, with a negative sign, of course. And then if you plug it back into 2, velocity of A after impact is going to be B prime minus 28, so it is going to be minus 49.1 meters per second. So look at what happens. This guy that was 30 now goes to 21.1 and still negative, which means to the left. This guy that was positive 40 now goes to negative 49. Yeah, so that shows you an important lesson. Never mess up with the semi, because the semi just goes from 30 to 21. Although it is hitting a truck, a big truck which is moving very fast, it's no match for the semi, okay? It just goes from 30 to 21, but the truck goes from positive 40 to negative 49. So you are going to be kicked back at more than 100 miles an hour backwards. It's pure suicide, basically, okay? So you should not mess up with a semi. Okay, so hopefully that's what we have learned. And then you can have tailgating accidents where now both velocities are positive. Tailgating is, accidents are not as bad as basically head-on collisions. And if you want, I can show you one case of that as well. So let's just say we have the sedan again. I just want to make sure that we go through these examples enough. So here we have the sedan again. And we make the mass of this, let's say 1,000 kilogram. And let's say the sedan is also moving with something like 30 meters per second. So this is what probably happens in Prescott, right? Or let's make it 20 to make it more realistic. So you are on the highway, 89, and then there is one of the sedans moving at 20 meters per second, and 20 is about half of 89, so it's about 45 almost miles an hour. You know, the speed of that highway is 65, but you see some of these people who don't want to move on the highway, they are only going at 45, and they are still in the left lane. They don't change lane. They want to keep on the speed lane, but not going fast. And then there is this trucker who is in hurry, and they want to go and do something, and guess what happens? The trucker will be surprised because this guy would not change lane and hit it from the back. Okay, so a tailgating collision. What happens in such case? Let's also look at the scenario together as well before we close this topic. So in this case, MA is 2,000, VA is positive 40, MB is 1,000, VB is positive 20, and then here we also have VB to be 20 and this guy to be 40. So this is 20, so that is going to be 8. And then here, if you simplify 3 zeros, you're going to get 8 VA plus 2 VB. Or no, actually, 2 VA prime plus VB prime is equal to AD plus 20, which is 100. And if we, again, what we need to do is to subtract 1 from 2 to get rid of VB prime, and then we're going to get VA prime times 3, right? It is going to be, that's 24, so you're going to get 76. So VA prime is going to be 76 divided by 3, which is 28.7. And then VB prime is going to be VA prime plus 8, which is 36.7. So what happens is this guy that was 80 now has to go with 28.7, but this guy that was 20 is now what? 36.7. So what happens? Yes, the truck will be slowed down by 11 meters per second. So it will definitely get a good shock. But this guy goes from 20 to 36.7, 16, 17 units, which is almost a little smaller than twice. So what happens? Yeah, you bring that guy to the speed of the highway. Now it's going to be kicked forward with twice as speed as it was going, and you slow down. Okay, but this shock is much bigger for this guy than you, of course, because you have a bigger mass and bigger velocity, which means bigger momentum. So hopefully this gives you a little bit better idea about impacts, direct central. Okay, now that we have seen this topic, it's time to look at the 2D version. And 2D version is oblique, when the relative velocity direction is not collinear with the line connecting the centers. Here the collision is 2 or 3D, depending on how we look at it. And here we define two new things. One is line of impact, the other one is plane of contact. So when these two objects collide, the plane, the 3D plane that is tangent to both of the objects at the contact point, we call it plane of contact. And then the normal line to this plane is the line along which the normal forces, the impact forces, are exchanged. So we call it line of impact. Clearly here, because we have a contact, the contact forces are exchanged along this line of impact. Here we might call it x-axis, so the forces are only exchanged along the x-axis. But this plane of contact that has y-axis on it, and if you look in 3D, it has also z-axis on it. Along the y-axis or z-axis, no force is exchanged. Therefore, only along the x-axis, because there is a force exchanged, the x components of the velocity will change. So what we do, for the x component of the velocities, we form the two equations that we just used in the impact problem for direct central. We're going to use them again. We say, in along x direction, since the forces are exchanged, but the total momentum of the system is conserved because those forces are internal, along the x-axis, the total momentum is conserved, and then I have the coefficient of restitution. So using these two coefficients, I solve for the x components of VA prime and VB prime. But then along y or z, or both, since there was no force, there will be no change in the velocities of any of the particles. So velocity a prime of y is the same as velocity ay, and the same for z. So none of these components are going to change because along those axes, no force was exchanged. Okay? So for y and z, basically we do nothing. We just say the components of these particles, each one of them is not going to change. For the x-axis, if x is the line of impact, then we say yes, we have to follow the same way we did for direct central. Now, the question is, when these objects hit each other, do they always come into contact like this, so that the x-axis is this horizontal and the y and z is vertical and z is normal to the plane? Is that always the case? The answer is no. Sometimes, like this example, if you draw the common tangent and the common normal to the balls at the contact point, it is tilted like this. So what do? We use tilted coordinate frames. Okay, we call this tilted axis X and this tilted axis Y instead of using the traditional X and Y. This rotated coordinate frame will help us still use these equations, okay, and makes life a little simpler. So what I'm gonna do right now with you, I first gonna go over this topic, which is important, especially for your project, and then we're gonna solve this problem together, and hopefully it gives us a lot better practice on the oblique impact, okay? So, and this is the solution process for oblique impact. I'm gonna follow these steps one by one when we go through this problem. So, but first, let me talk about this important thing. When the impact happens and one of these two objects of impact is a fixed object, like the wall or ground or something like that. Like for your project, let's look at your project. So for the case of your project, when this projectile comes and hits the ground here, right? So whenever it comes and hits the ground, if you calculate the velocity of the projectile right before it hits the ground, okay? So we say we calculated at the time of impact with the ground, the velocity of the particle was v, and this angle of impact, which we measure with respect to the x-axis, this was theta or alpha, whatever you want to call it. So we could calculate both of these from the projectile motion equations. Now, I also am given E. E of the impact is given, like your project. I want to know with which velocity does the ball bounce back. So if it bounces back and it starts another projectile, which goes until next bounce, and I call this V prime, and I call the angle of bouncing back, the next projectile launch angle basically, I call it beta. I want to know what is beta and what is V prime if V, E, and alpha are given. Again, alpha and V are coming from projectile motion, E is given, right? How do I find V prime and beta so that I can calculate the next projectile and the next and the next and the next? So what do? So here, if you see the plane of contact, the tangent to both surfaces is the horizontal line. And the normal line along which the force is applied is what? It is the vertical line. So in this case, actually, you might say, well, I want to use x-axis to be vertical and y-axis to be horizontal according to those formulas. Yes, you definitely can do that, but in this case, since it's so simple, you might still keep your x and y axis as is. So don't change them. Use the same x and y that you use for projectile. But know that this x is now plane of contact or line of contact. Let's just write it like that. Plane of contact. And the y-axis is line of impact. So if you want to use those equations that I just showed you, you have to reverse some order, right? You have to say my x components of the velocity don't change, but my y components, I follow these equations. And by the way, when one of them is stationary, it is a stationary regardless of the impact. So in other words, if here you call A to be your projectile and B to be what? The ground. the ground will have no velocity before or after. In other words, VB prime is the same as VB, and that is the same as 0, right? The ground does not move due to this impact. So I know this. And so one of the components of the velocities after impact is already there, so I don't need two equations. All I need is one equation from these two. Which one? The E equation. You're going to use the E equation. Now, if you look at the E equation, as I said, I'm going to write it about the Y component here. So I would say E, which is a given number, is negative VB prime Y minus V prime A Y divided by VBY minus VAY. Again, because the impact is along Y, and then you say, well, VB is 0, regardless of it's on the x-axis or y-axis. So these guys are both 0, and therefore, if I solve for VA prime of Y, it is going to be negative E times VA of Y. And what is VA of Y? Right? VA has magnitude V, and it has angle alpha, so the Y component is going to be V times what? Yes, sine alpha. Right, this guy here. This is V times sine alpha. And since it's downward, it is negative. So what is this? This is negative V times sine alpha. So if you calculate, cancel out the negatives, you're going to get E times V times sine alpha. And it is positive. Is that correct? Yes, because if you look at the component of V prime, which is the same as V of B, clearly you see the Y component is what? Positive. Right? Now what about the X component? You say the X component for the projectile is not going to change. It's going to be the same as what it was before impact. And what was it before impact? You see it was V cosine alpha. Right? So here, you see that I could find my X and Y component of the projectile right after the impact. And if I want to find from these two the magnitude and the angle of VB prime, all I need is to use what? The magnitude formula and the angle formula. So this is going to be square root of V prime X squared, right, plus V prime A squared Y, which is going to be V times square root of cosine squared alpha plus E squared sine squared alpha. And if you want angle beta, it is going to be tangent inverse of V prime A of Y over V prime A of X, which is going to be E times tangent, going to be tangent inverse of E times tangent of alpha. And since E is less than 1, beta is going to be less than alpha. And since, again, E is less than 1, V prime is going to be less than V. So clearly, this is going to be less than V, and this is going to be less than alpha. If you found bigger bouncing velocities or bigger bouncing angles or projectile angles after impact, something is wrong. Something is messed up. Okay, so please keep that in mind. These are what you would use for your project. Now you might wonder, where do I use them in my project? If you remember, in your project, you have an M file, right? So if you remember, in your project, you have an M file here, and then you have what? A Simulink, correct? So this is your Simulink. This is your M file or script. Now, how do you use them together? In script, you set up your parameter values, which are like E, and anything else other than V that is needed. Then you set up your initial conditions, right? Or if you want, you can do it in a loop and start it. So inside the while loop, you set up your initial conditions, which is what? X of launch point, Y of launch point, V of launch point, and theta of launch point, right? And then you let the projectile go forward. So when you have the parameter set, and again, parameter that we have in this problem is E, I assume, and then there are some other parameters that you can see in the project file. So if you go under modules and project, and you look at the project description, there are some other parameters that you need. One of them is to calculate the mass of the projectile that you need. And how would you calculate it? You have, it's a sphere, the radius is given from which you find volume. The density of the steel is given, so if you multiply the density by this volume, you would get mass of the sphere. Then you need a drag coefficient, you need a density for the air, and you need the initial spin of the projectile. So here you assume that every time that the ball is hitting, you have the spin. Although this is way more complicated than that, even if initially you give it a 20 radian per second spin, when it hits the ground, it's not going to keep this 20 radian per second spin. It is going to change. But here we assume that throughout the travel of this ball, this spin is going to stay the same. It's not really, but again, we just go with a little bit more realistic than the simple formulas we had. So this project is not 100% realistic because the lift formula will change, and then E each time, as I mentioned in the previous lecture, would change. But here we just use a fixed E of 0.6. And where do you need that density of air, drag coefficient, and spin? You need them in the formulas to calculate the magnitude of the drag force and the magnitude of the lift force. So the magnitude of the drag force is half of the coefficient of drag, which for a sphere is 0.5. This coefficient depends on the shape of the object. And it's not even just shape, it also depends on how fast the object moves. So this CD is not actually a constant number for a sphere. A sphere that is moving faster or the one that is moving slower, they have different CDs. But again, here we assume that it's constant. So you see, a simple projectile problem, and then when it hits the ground and keeps going, if you just want to simulate that according to the real life, there are a ton of more variables that even here with this complicated MATLAB simulation, we're just throwing them away, or not throwing, we just neglect them, right? One is CD is not constant, E is not constant, the spin is not constant. We neglect the effect of a side wind or any turbulence and so many other things. Okay, so it is quite complicated. We are neglecting gyroscopic effect and so many other things. The Magnus force that I showed you. So the magnitude of drag force is half of CD times rho. Rho here is rho of the air. It's the density of the fluid in which you are moving. A is the section area of the object, which is basically pi over 4 d squared, or pi times r squared. R is 2 centimeters. And v is the velocity of the projectile, which comes from the square root of x component, x dot squared, plus y component of velocity, y dot squared. The formula for lift is 16s times rho. Again, rho here is rho of air, s is the spin. Pi r squared, r is the radius, and v here is again magnitude of velocity. You see, lift is proportional to velocity to the power 1, while drag is proportional to velocity to power 2. By the way, the angle theta, the angle of the projectile at each point, is tangent inverse of y component of velocity, which is y dot, over x component of velocity, which is x dot. So you see the angle does change versus time because y dot and x dot does change. And the velocity does change at every point versus time. Okay? So when you plug these guys back into the two governing equations for the x and y direction, you're going to get two second order nonlinear ODEs. Clearly you see there is tangent inverse, square root, and so many things. They are nonlinear. Cosine of tangent inverse is in it, or sine of tangent inverse. Not only that, they are coupled together. You cannot solve each one of them separately, because in the x governing equation, you have what? You also have y dot in v and theta. And in the y governing equation, again, you have what? X dot. Again, in theta, fd, and fl. So you have to solve these two ODEs at the same time. Both second order ODEs, both nonlinear, they have to be solved simultaneously. And you need a bunch of parameters. So the parameters, again, in our problem are going to be R, E, S, rho steel, rho air, and CD. So if I want to write them for you here, it's E, right? Then you have radius, then you have CD, then you have rho air, then you have rho of steel, correct? And what else? Spin. So you set up these 6 parameters and assume that they are not going to change during the simulation. Then in a while loop, what is the stopping condition? We're going to talk about it, but in a while loop, for each projectile, you set up the initial position, the launch velocity, and the launch angle, and then you call what? You call the Simulink with these initial conditions and say, hey, you keep, so here you have a bunch of wirings, right? So here you have a bunch of integrators that you know, and these integrators will give you some x and some y, correct? At the end, the double integrators. If you wire them correctly, this one gives you x, this one gives you y. And you say, hey, keep going until what? Y is less than 0. When y is less than 0, then what would you do? You stop, right? So anytime it hits the ground, you stop. And then export these back to what? To the workspace. So this data are going to come back to the workspace where this guy can access. Good. So what now? So I set up my initial conditions, I called the Simulink, I got my x and y, and now I'm going to store my x and y in a big array. and then I clean the workspace, clean the workspace other than, of course, the x and y that you just got, and the x dot and y dot. By the way, not only you need x and y, you also need x dot and y dot, and I'll tell you why. So you clean and make it ready for the next simulation, and then now that you have those, you keep repeating, right? And then once you have all the data, then you do your animation, of course, at the end of the loop. So first, when is it that you would stop? You would stop when the velocity of the impact, or the velocity of the launch, doesn't matter, the launch velocity, is too small. So you say, while the magnitude of V is bigger than some threshold, and you determine the threshold, but don't make it too big, something like 10 to the negative 2, 10 to the negative 3. While the launch velocity is still big, keep simulating. Once it's too small that I neglect the bounce, then stop it, right? So now the important thing in this problem that is related to impact is here. When the impact happens and you go to the next projectile and next and next and next, how do you update your initial conditions? That's the effect of impact. How do you do that? So if you look at your case here, or let me show it somewhere else. Maybe I can do it here. So here is the initial location, right, that you started, let's say 0 and 0. And you have some projectile and it comes and hits here. And your Simulink detect that y now wants to become negative, so it stops it. Then it bounces back and it goes here now and keeps going, right? So here what you have are x0, let's say, equal y0 equals 0 if you put the y-axis here and you put the x-axis here. So you say, for example, my initial launch position is 0, 0. Then my initial launch velocity is v0, which you determine, and my initial launch angle is theta naught. Right? So this is how you set it up. Good. Now, when it hits, and again here you have to provide another set of initial condition, you reset it. How would you reset it? Because here you have to provide again x0 to the Simulink, a y0 to the Simulink, a v to the Simulink, and a theta to the Simulink. How do you do that? Well, here, when you start again, y is again 0. You are starting from the ground. So this is not going to change. But your x is not 0 anymore. You have moved this much. So if this distance is whatever you want to call it, L, so now you say my x0 is what? L. The range of the previous projectile is L. And how would you find it? Well, from your Simulink data, right? If you go back, let's see where it was. This guy is sending you back all of its x, y, x dot, and y dot simulation. And it stops when? When you hit the ground. So if I can look at the x data that it sent me and find the very last x point, right before it hits the ground, that is actually this x. So this is x at what? End. You know, end in MATLAB means the last entry. What about v and theta? V and theta I have to find them through those equations that I gave you, right? V after impact is V before impact times square root of what? Cosine squared alpha plus E squared sine squared alpha. So how do I find it? I need to find V right before impact and then multiply it by this number also. And what is this number? Here alpha is the angle right before the impact and V is the velocity right before the impact. And E is a constant. So before I can calculate V prime first, I need alpha and V and also beta. So the first thing you do when you come down here, you need to first calculate your V and alpha. V is square root of x dot squared plus what? Y dot squared at any point. But which x dot, which y dot? The one right before impact. So this is going to be x dot at the end squared plus what? Y dot at the end squared. And alpha, which is the angle, it is going to be tangent inverse of y dot at the end divided by x dot at the end. So these are the numbers before impact. Now you say the new velocity, which is v prime if you want to call it, in theta prime, or in the notation that I just did, I call it beta, it doesn't matter. This is now v times square root of cosine squared alpha plus E squared sine squared alpha. And this is tangent inverse of E times tangent of alpha. And now with these four initial conditions, you run your next projectile and then keep repeating it. Okay, so hopefully now you exactly know how to solve your project, because I wrote for you basically all the formulas. I wrote for you the flowchart and everything, right? So here you have the basically diagram, the logic of your coding, and then I gave you animation examples, I gave you Simulink examples, several. So doing the project should not be really a hard thing at this point. Okay, so now going back, I actually was double thinking, and I would like to let this problem 1679, the oblique impact, to be solved inside the class, as we spent a good amount of time on solving direct impact problems and going over project. And we have some good time in the class too, so I would leave this for inside the classroom, and we're going to go over this problem inside the class. What I would like to do is go over 16.3 and finish up chapter 16 in this lecture. So the new notion, the new topic that we have to talk about is a new type of momentum called angular momentum. So far we learned about linear momentum, which was mass times velocity. And from our intuition, we know that we know the notion of inertia, right? So let's 1 second very fast mention inertia. So this term that we hear a bunch, inertia. Inertia means what? Means the lack of tendency to change the current status of motion, okay? Unwillingness to change the current status of motion. So whatever you were doing, in whichever direction you were going with whatever velocity, you want to keep doing that. You don't want anybody to disturb you and tell you to go in a new, different direction with a different speed. Okay, but as you know, there are two types of motion, and we're going to see it with more detail in chapter 17. But there are two types of motion which we're going to see. One is called translation, and the other one is called rotation for a rigid body. And rigid body, we know, is an object. The distance between any 2 points of it is not going to change. So translation means an object goes from point 1 to point 2 without changing its orientation, okay? And as I'm going to show you in the future in chapter 17, any two arbitrary points, if you consider any 2 points on this rigid body, the displacement of those points between the 2 time points is going to be the same. Okay, so if this is called delta r of B and this is called delta r of A, if these two are equal for any 2 points, we call it pure translation. Now, on the other hand, if I have an object and then some points on this object or on the extension of this object, in theory, can, let's see if I can rotate this guy. I don't think I can. So some points on this object might not move at all, and on the other hand, some other points of this object, they move, and the amount that they move is not the same. So we cannot say any 2 points on this object are moving the same amount. So here you might say this is point A, this is point B, this is point C. And when this object is rotating this angle theta, then point A does not move, so A and A prime are the top of each other. B moves, and then C moves more. And so you see, as I move away from this center of rotation, as I move further away from it, the displacement is linearly getting bigger and bigger, which means if I get away 2 times more, my displacement is going to be 2 times bigger, and so on. That is called rotation. Now, against each one of these types of motion, there is an unwillingness, a lack of tendency. If something is moving straight, it doesn't want you to change its velocity, and if you try to do, it shows a resistance. It doesn't like it. How do we measure that resistance, that lack of tendency? By an inertia. Inertia that an object has against translation, what do we call it? Yes, something that you have seen a ton so far, mass. Right? The heavier the object is, the harder it is to shove it around. You cannot do that easily for a huge, massive object. But there is another type of resistance that the object shows if you want to change its orientation and rotate it with a different angular velocity or in a different direction. That is what you learn in your statics, and that is called what? Mass moments of inertia, the unit of which was kilogram meter squared. So these are the 2 inertias, right? Rotational inertia and translational inertia, or mass. Hopefully so far so good. Now, similar to that, the momentum also, the momentum that we learned, so far we learn only momentum for translation. If the object is showing some linear motion with velocity v, then this momentum is going to be its inertia term, mass, times its velocity terms, v. Okay? So momentum is always the product of what? An inertia term and a velocity term. Now we're going to see what about if the object does rotate. If the object does rotate, I also define a momentum for it, and I show it by letter H. And this H, like torque, it needs a reference point. So here, let's say the reference point of me is the center of mass for the object. And then this guy is going to be the inertia term again, but this time rotational inertia, which is I, about the center of mass, and then the angular velocity instead of linear velocity, or I omega. I'll show you later, not right now, but I'll show you the angular momentum for a rigid object, rigid body, can also be defined this way. And we're going to see that. Again, it's the product of an inertia and a velocity term. But right now, what we want to do is not rigid body, because right now we don't have a rigid body. We only have a particle. So we're going to introduce this H in a different way, in the original way, and then later I'll show you whatever we do and we introduce here. For a rigid body, you can convert it into I times omega. So don't be surprised if the definition you see right now is different from here. So angular momentum. First, why should we even define this? Where does this come from? Well, let's see. Where did we see this linear momentum anywhere in physics? Why did we decide to introduce this quantity? Because we just don't multiply some quantities together and come up with a new one. There has to be applications for that, right? We don't like to introduce more and more parameters and more physical quantities unless they have a physical meaning and they appear in a bunch of formulas here and there. Then we give them some formality, right? So why did we decide that this linear momentum is an important thing? Because it shows itself in what? In second law of Newton. It says rate of change of this guy is the forces that are applied to the particle. Now what about this H? Does it show itself somewhere? Yes, let's see. So what we do here is we again start with the second law of Newton, F equal ma, and we assume here the mass is constant, so instead of dp over dt we say mass times A. And what I do, I cross multiply both sides of this by vector r. And you might say, what is vector r? So vector r is the position vector of your particle, right? You know, any particle has a position vector with respect to the origin. So what I'm gonna do is I use this vector r and then cross multiply it by what? By summation of the forces on the particle and by this mass times acceleration. And for acceleration, if you don't mind, I write it as dv over dt. Good. So now I'm gonna do something. What is this right-hand side? Let's take a look. In order to look at this right-hand side, I do some arithmetic, or not arithmetic, vector manipulations. I take time derivative of r cross mv. What do you think would happen if I take time derivative of r cross mv? Since this is a product, it's going to be derivative of first one cross the second one plus first one cross the derivative of second one. But this dr over dt here is what? That is v, right? That is v, velocity. So what you have here is v cross mv. And you know m is just a constant positive number. So it can get out of the cross product. So you're going to get m v cross v. And what is any vector cross itself? You know, it is 0, right? Because the magnitude of the cross is magnitude first one, magnitude second one, sign of angle in between. Here, sign of 0 is 0. So this first term is 0. It's going to go away. I'm only down to the second term. And what is this second term? That's what I had here on the top. So it should not matter if I replace this term in this top equation with d over dt of r cross mv. So I put it up there. So this right-hand side is time derivative of something. That's the right-hand side. What is the left-hand side? The left-hand side, I bet you know the meaning. What is the position vector cross force? Yes, that's what you learn in your statics as what? Torque or moment, right? That's moment. That's what you learn. Moment. M. If the force is applied at some point and the position vector of that point is r cross f is what? Moment. So this r cross f, I would call it what? Sum of the moments about point O. And then you remember that the right-hand side was this d derivative. So it was the time derivative of something. Now I call this new something r cross mv. I call it h, angular momentum. And since r, the beginning of r, the reference for r was origin, I say this h is measured with respect to what? Origin. And I call this guy angular momentum. So first thing first, the definition of angular momentum is this. If you have a particle with mass m with velocity v, and the position of the particle with respect to point O is r, then r cross mv is what we call angular momentum. But what is mv itself? If you remember, mv is linear momentum of the particle. So it says angular momentum is what? Position vector cross linear momentum, okay? So if instead of this, I choose my reference point to be origin instead of centroid. So I say, well, h, the way I define it is the position vector r cross that p, or r cross mv. This is how I define angular momentum at the moment. And I'll show you later, you can convert it to what? I-O times omega. So for the moment being, if you don't mind, I get rid of this, because we're going to see this later. And I bring this guy up, because that's how I want to define angular momentum at the moment. Good? One thing is, first of all, this angular momentum always needs a reference. You never say h. H by itself has no meaning until you say with respect to which point. Why? Because this vector r is drawn from point O to the current location of the particle. If you draw this r from another point O prime, then this should be h with respect to O prime. So wherever is the beginning of vector r, that would determine the reference point. And you should always mention a reference point. Good? Now, what's good about this? We have seen here in this proof that some of the moments applied with respect to the origin, right, r cross f is sum of all moments applied about origin is equal to what? D over dt of HO with respect to d over dt of HO. So let's see. I can see that sum of all moments with respect to point O is d over dt of h with respect to O. Do you see similarity here? What makes an object translate? What is the cause of translation? Yeah, you would all say what? When is it that the object translates? When you apply a force to it, right? When you apply a force to an object, it will translate. And when it translates, it gains what? It gains linear momentum, right? This second law of Newton is relating the cause and effect. This is cause, the cause of translation, and this is what? The effect, gaining momentum. Yes? Now what about rotation? You learn in your statics, what is the thing that makes an object rotate? Yes, it's moment, correct? So if I call this point O, what makes this bar rotates about point O? You know, there should be a moment. It could come from a force, right? It could ideally come from a force like this. But that force creates, with respect to O, a what? A moment, right? And that moment is what makes rotation about point O happen. Now, when you rotate about point O, you gain something we call what? Angular momentum, which, by the way, is about the same axis, perpendicular to the board. And again, I'm saying that the rate of change of that angular momentum now is equal to what? The cause of rotation, which is moment. So again, this is the cause of rotation, and the effect is angular momentum. Okay, so you see the governing equations for translation and rotation are very similarly defined. Perfect. Now, the angular momentum clearly has unit of length times linear momentum. Linear momentum was kilogram meters per second, so this is going to be kilogram meter square per second. And then, if you want, you can basically cross multiply both sides of this new equation that we got. If we cross multiply both sides of this new equation by dt, you would get sum of the moment about O. dt is equal to d of h with respect to O. And then you can integrate both sides again with respect to time, the left side, and with respect to angular momentum on the right side. And what happens if you do so? Then this is similar to linear impulse, right? Remember, linear impulse was integral of force versus time. This is integral of moment with respect to time. So this one, I'm not going to call linear momentum impulse. I'm sorry. I call it angular impulse, okay? And again, there could be different symbols. Your textbook did not really provide a symbol, and I avoid to do that. So here, this is going to be HO2 minus HO1. So what is this here? On the left, this is again a new quantity, which we call angular impulse. Which is the area under the curve of moment versus time, and this is what? The change in angular momentum. Just like the linear impulse and momentum formula that we had, right? Remember, here what we did was we cross-multiplied both sides by dt, and then we integrated with respect to time on the left and p on the right, correct? Yeah, so you now see all the similarities. This one was linear impulse, was equal to the change in linear momentum. And the angular impulse is equal to change in angular momentum. So whether you use this one or this one for rotational translation, or the equivalent version of them, which is this guy or this one, you clearly see the similarity of the governing equations for translation or rotation. So now that we have seen this topic, there is one simple problem that we can solve before this lecture ends, and that is problem 1693. So you might wonder, okay, where can I use this, any of these two equations, especially this new one, principle of angular impulse, angular momentum, where can I use that in any particles problem? So that's one example here. So you have a disk, a table that is horizontal and it's smooth, means there is no friction. There is a hole at the center, and then through which you pass this rope and you connected this small object with the mass of 1 kilogram on it. And so it is connected through the rope, through the center of the hole. The radial distance from the center, you call it R. And it's not necessarily physical center, it is just the pivot point, the point about which the disk rotates. Now, you want to know if this mass moves in a circular path with constant R of 1. So you don't let the R change, you keep it at R equal 1, and you turn it such that the velocity, which is V equal R omega, is 2 meters per second, which means basically your omega is 2 radian per second. How much tension you need to make that circular motion happen? 1. 2. Now, assume that you don't keep the T constant. You do not keep the T constant when R is equal 1. Instead of keeping it at the constant number that you're going to find here, you keep increasing it. When you increase the tension, not only it is sufficient to provide the circular motion, it actually starts to pull in the disk toward the center, and so the radius starts to shrink. And you keep doing that until it shrinks to 0.5 instead of 1. During this time between R of 1 and R of 0.5, find the necessary tension as a function of radius. So if radius is somewhere between 0.5 to 1, how much tension do you need as a function of radius? Okay, because tension will depend on how much radius you have here. What kind of function is that? So let's look at this problem together. And again, let's see if I can copy this guy. And we go here and we paste it. Make it bigger. We write down whatever we know. So the surface is smooth, no friction, that is important. And M is 1 kilogram. In part A, it says that R is 1 meter. And the velocity of the particle is 2 meters per second. How much is T? So if you draw the free body diagram of this object, as you look at it in 3D, the same way it is right now. So the forces that are acting on the object, as always, is mg. There is a normal force from the table. And then there is a tension in the radial direction, and there is no friction, so that's all. And then you use some coordinate frame. Here I would like to use the NT coordinate, and here I assume that it goes counterclockwise like this. It doesn't really matter. And so this direction will be the ET direction, and this direction in toward the center, which is the t is also, it is en direction. So this is my FPD, that is my coordinate frame, and then on this vertical here, ET cross En, this is EB if I need it, right, by normal. So all I need here is to apply the governing, the second law of Newton in the n direction, which says sum Fn is equal to MAN. And here the only Fn you have is T. M is 1 kilogram, and you know An from your previous chapters, it is V squared over rho, or in this case R, right? So it is going to be 2 squared over 1, so you're going to get 4 Newton. You need 4 Newton of tension to make it happen. This part A does not need any principle of impulse momentum. You can easily do it with the Newton's second law. But now for part B, which is the interesting part, it says the free body diagram stays the same, the coordinate system stays the same, but this time it says now the R is somewhere between 0.5 to 1. What is T as a function of R? Okay. Clearly the V is not 2 anymore, because V also does change. So what do we do here? And how do we approach this problem? So what we do, and we're going to use this formula that we learned, we are going to apply this formula which says the angular impulse is equal to HO2 minus HO1. So let's write it down. And here I call this center point point O, if you don't mind. So I say the integral of some of all moments about point O dt from T1 to T2 is equal to HO2 minus HO1, right? And since I'm writing everything here about this EB, right, everything will be about the B axis. So because the moments that I'm going to calculate are going to be about B and the momentum. So everything is going to be a B component. Everything is going to be about the binormal direction here. So everything is B, therefore everything is a scalar, and I don't need anything in a vector format. Good. Now, for this free body diagram, what is sum of the moments of these three forces with respect to the B axis that is passing through O? So this is my axis, right? With respect to this axis, which one of these three forces is creating any moment? We know none of them do, right? Because N and mg are parallel to the axis and T will intersect the axis, right? So that is T, that is N, that is mg. You know, only under one condition a force can create a moment about an axis. What is that? So if this is an axis and this is a force, this force can create a moment about this axis if and only if, let's say the unit vector of this axis is u, F can create a moment about this line with unit vector u if and only if what? F and UL have to have one condition. They should not be intersecting, they should not be parallel, they should be skew. And skew means the two vectors that are not on the same plane. You can never pass a plane from the two vectors, okay? So they are not parallel, they are not intersecting, then we call them skew, right? So no plane can pass here from U and F. And in this case, if you look, N and mg are parallel to this axis, B and T is I'm looking about this axis here. And t is passing through it, so this guy whole thing is 0. And when that's the case, it means HO2 for B is the same as HO1 for B. And how do you find HO based on our definition? H is R cross MV, right? It is R cross MV. Now, in this case, if you just look at magnitude of HO, what is magnitude? So magnitude of a cross product, because we are now looking at magnitude, magnitude is what? Magnitude of the first vector times magnitude of the second vector times sine of angle in between these two vectors, if there is an angle 0, 90, whatever. What's the angle in this case? So in this case, the velocity is like this, right? We know the velocity, since it's going on a circular motion, the velocity is always normal to the radial line, so that is your velocity. And this vector here in red is your position vector, right? This guy in red is your position vector. Clearly, you see R and V are perpendicular to each other, so the angle in between is 90, and sine of 90 is what? 1. Therefore, the magnitude of R cross MV is simply R times MV. So this is going to be what? R times MV2 is the same as R times MV1. But what would you consider 1? What would you consider 2? So I consider the initial situation 1 when R is equal to 1 meter. I consider it situation 1. And 2, I consider it when it's an arbitrary R meters, where R is between what? Between 0.5 to 1. I'm not considering 0.5. I consider it arbitrary R. Why? Because T is needed at arbitrary R. So 1 and 2, I choose arbitrarily myself. Now, in position 2, your position vector, in configuration 2, your position vector has magnitude of R. The mass is still m, and the velocity is some v. Let's call it v2. In position 1, your R is 1 unit, your mass is still m, and your velocity v1, right? Your velocity v1, so this is r1, this is r2. Your velocity v1, as you know, is 2. So it is going to be times 2. And if you cancel out m's, from here you can find v2 as a function of r. v2 is going to be what? 2 over r. So clearly you see, when r is not 1, your velocity is not going to be 2. It is going to be, since r is less than 1, it's going to be bigger than 2. And that's quite obvious. When you pull the object in and the circle goes in, you have the chance of higher velocities, right? Because you're increasing the tension. Okay, that is V. And now, if I go back here and look at this FBD again, but this time for situation 2, this equation is still valid for situation 2, right? This is still valid, but the only difference is V is not a constant and R is a parameter. So if I apply this guy one more time for situation 2, what would happen? Actually, you know what? Let me use I use the final thing that T is equal to mv squared over r. So T, which is a function of r, is equal to m times v at that position squared over r, right? And if I replace, this is m, which is 1 unit, I assume, right? Was 1 unit. And then v is simply 2 over r squared and then divided by r, so it is going to be t2, which is the same as t of r, is equal to what? 4 over r cubed. Where r is anywhere between what? 0.5 and 1. So if you want to shrink the radius to radius r from 1 to an arbitrary radius r, which is bigger than 0.5 in this case, you have to change the tension at every time. And how would you change it? By 4 over r cubed. In other words, if you make r 2 times smaller, you need 8 times bigger tension. So if the tension at 1 meter was how many newtons? It was 4 Newton. At 0.5, if you plug in 0.5, what would you get? 8 times that, 32 Newton. Okay, so that's how you should change T. Okay, I assume I have covered chapter 16.